Alright guys, so today we're going to be starting our actual calculus. So there's a couple of sections of calculus, and the first of these sections we're going to look at is something called limits. Now we've actually already started to look at limits so far this year. But to start off, we're going to look at a function that we've seen. This function is the rational parent function, which is 1 over x. So one of the things we looked at with this function earlier this year is we talked about what happened on this graph as my x approaches infinity. So as my x's get bigger and bigger and bigger, what are my y's getting closer to on this graph? And if you look, these x's, as they keep on continuing towards infinity, they're going to keep approaching that horizontal asymptote there at 0. So my y's are going to get closer and closer and closer to 0. Now what we're going to do is we're going to rewrite that as a limit. So what this actually means is the limit on this graph as x approaches infinity. So as my x's approach infinity, on the function 1 over x, which is the function I have, that limit is 0. So as my x's get bigger and bigger and bigger, my y values approach 0. So the limit really is what as your x's approach a certain value, what do your y values approach as well. In the general format you'll see a limit in is something like this, where you'll have the limit as x approaches some value of some function in terms of x, and that's going to equal that limit. Okay, so another one we can look at, instead of, we're going to actually write this in that limit form, if I do the limit as x approaches negative infinity. Again, if I look at this graph, as my x's go towards negative infinity, those y's are still approaching that same asymptote, so the limit of this graph is also 0. Now, it doesn't necessarily, though, have to approach an asymptote for us to be able to find a limit. Let's say, for example, I want to find the limit as x approaches 1. Now, if you look, I went ahead and made that as a point on my graph so it's a little easier to see. When x is 1, it's actually equal to that dot right there. But to see what the limit is, we're going to see what my graph, again, approaches as I get close to that point. So I look at the right side of this graph first. As I follow the right side of this graph closer and closer to that x value of 1, my y's are approaching 1. Then I look at the left side of my graph. As I go on the left side closer and closer and closer, my y values again are approaching 1. So in this case, the limit as x approaches 1 is equal to 1. And that's actually the value of 1 as well. Now that doesn't have to be true, but sometimes it will be true. Okay, to see this again, I'm going to show this to you guys on the calculator, so you guys can see as well what we were just talking about. Alright, so here's my function. This is y equals 1 over x. So what I'm going to do is I'm going to go and try and type in some values. So just like we were looking at the graph, we're going to pick a value really close to 1, but we're going to look at it from the right side. So on the right side of 1, a value that's pretty close would be 1.1. So if I type in 1.1, I get 0.9. So now I'll move closer to that value. I'll do 1.01. And then I get 0.99. Okay, even closer, 1.001. I'm getting closer and closer and closer to the actual value of 1 on the right side. Okay, now let's look at the left side. So a number just to the left of 1 would be like 0.9. 0.9 gives me a value of 1.1. Alright, let's get closer. Let's do 0.99. There's my y value, again closer to 1. And then even closer, 0.999 as an x value. I'm practically at 1 as an x value. And again, my y value is still even closer to 1. So both sides of this graph, as my x gets closer to 1, the y's are getting closer to 1 as well. And that's why it's my limit. Alright, so sometimes we're going to look at these graphs without actually having a graph there. We're just going to look at the actual equation. So this first equation that I'm going to look at is going to be the limit as x approaches 1 of x squared plus 3. Now you guys know that kind of a graph, it's a parabola, it's a quadratic function. So there's not going to be anything weird in this graph we have to worry about where it's going to approach different values, or any holes or asymptotes or anything crazy happening here. It's just a normal parabola. So what I'm going to do is I'm going to take 1 and I'm going to plug that into my equation. So when I do 1 squared plus 3, I get a value of 4. So when x is equal to 1, y is equal to 4. Well, in this case, since my graph isn't going to do anything weird, if my x value, when x is 1, if I actually get a y value of 4, I know both sides of that are also going to equal the same thing. So sometimes all I need to do is just take that value and plug it in for x. Alright, so now I'm going to try this next one down here. I'm going to start this off the same way. I'm going to take negative 1 and I'm going to substitute that for x. So if I take negative 1 and I plug that into the top, I get 0. Then if I plug it into the bottom, I get negative 1 squared, which is 1, minus negative 1, minus 2, which also works out to be 0. Now if you get 0 over 0, that's a very special kind of a limit situation here. The form that this is in right now, this is not your answer, this is just the form the limit's in right now. This form is indeterminate, which means you are unable to determine anything right now. We cannot tell what our limit is with our graph or with our equation in the form of 0 over 0. So if you get something like this, indeterminate's not your answer, it's just a clue to you. It means you need to do something to change the equation. So I can't find my answer as is, I need to do something else. I need to change that equation somehow. So what I'm going to do is I'm going to factor. So the bottom here, this can factor into x plus 1 and x minus 2. And those x plus 1s are going to cancel out. Remember, when they cancel out, they don't disappear. I'm left with 1 over x minus 2 now. So now what I'm actually finding is the limit as x approaches negative 1. And now I can take that negative 1 and plug it in. So I get 1 over 3, and that fraction is negative. So that's my limit. Now we've talked about this a little bit before. When that factor cancels out, it actually creates a hole in your graph, which we're going to talk next week about how that's a removable discontinuity. But remember, when it creates a hole, it doesn't actually mean that negative 1/3 is the value like it was for 4. But that's okay. Again, it's what my graph is approaching and coming close to. So it doesn't have to necessarily equal it, it just needs to be, as my x's get closer to the value of negative 1, what my y's get close to. It's okay if it equals it or if it doesn't equal it. Now the last one we're going to look at, so what I have here is a piecewise function, and it's just showing us the graph. So remember, piecewise functions you learned about in Algebra 2, that's where you have a certain function in one section of your graph and a different function in the other. So like this graph right here, the first limit we're going to find is the limit as x approaches 2. So the x value of 2 that's my location. So I'm going to find where that is on the graph, which is that point right there. And what I'm going to look at is the right side of this graph, that right side, and see what value it's approaching, and the left side and see which y value it's approaching. Both sides are approaching the same y value, and that y value there is negative 3. So that's my limit. Now I'm going to look at the limit as x approaches negative 1. Alright, so at negative 1, something a little bit different is happening here. So the x value of negative 1 is that location. So let's look at the right side first. The right side of that point is this bottom part of the graph, and it's approaching that open circle. Even though it doesn't touch that open circle, it's okay because that's what it's approaching. And that y value that it's approaching on the right side is negative 3. Now we're going to look at the left side. So the left side of the graph is that closed circle up there. And it's approaching that value, and that value is 2. So the left side of my graph is approaching 2. Now the problem with this equation, though, is if my left side and right side are approaching 2 different values, how can I tell what that limit is? How can I tell what the equation as a whole is approaching at that point? And the problem is I can't. So what we say here is, we quote Mean Girls, and say that the limit does not exist. Now one thing that I do want to look at in this is, let's say I wanted to actually evaluate this function, and let's say I wanted to find the value of the function when x is equal to negative 1. Even though the limit doesn't exist, that's something I can find. And f of negative 1 is where this graph actually has a closed circle at negative 1, which is the y value of 2. And we're going to talk about that a little bit more next week. Alright, so the last thing I want to look at is the 3 cases where a limit does not exist. And the first one we just looked at. The first one is in my left side and right side approach 2 different values. So if my left side and right side approach 2 different values, I cannot find what that limit is. All right, another case is like the first example we saw, where if my graph is unbounded. And unbounded means it doesn't ever really approach anything. It keeps on going towards infinity. So for example, if I wanted the limit as x approaches 0 of 1 over x, that limit does not exist. Because that graph would look like this, and at 0, I'm going towards an asymptote, which means it's going to keep on going to infinity. Now I can describe that behavior and say maybe from the right side of that it approaches infinity, and from the left side it approaches negative infinity. But because it doesn't actually reach anything, it doesn't really have a limit. So the limit doesn't exist, but we can describe what it's going towards. And then the last case, you're not going to see very much, but if your graph is oscillating, then that limit also does not exist. And we're going to look at an example of this on the calculator, but that would be something like, if we want to find the limit as x goes to 0 of the function sine of 1 over x. So what I'm going to do is I'm going to graph the function sine of 1 over x on the calculator so you can see what that one does, because it's a little bit different. Okay, so when we graph this function, it's kind of hard to tell right here. I am going to plug in some numbers so you can see what happens. But if I plug in, let's say a number from the right side, like 0.01, I get a negative 0.5. Then if I do 0.001, I go up to 0.82. And if I do 0.0001, I go back down to a negative number. So it's really hard to see what this graph is doing because it keeps going up and down between negative and positive. So what I'm going to do is I'm going to zoom on this as well so you can see what it looks like. Okay, so here's zoomed in to where I'm going from negative 3 to 3. Okay, I can't really see exactly what it's doing, so I'm going to zoom in a little more. And now you can get a pretty good picture of what it's doing as it gets close to 0. I'm going to zoom in one more even. So you can see at 0, this graph is going crazy. It keeps going up and down and up and down and up and down. And if you think about this window right here, look how small that range is. That x-min right there is only at negative 1.1. So I don't have a very large portion of this graph, and it's going up and down that many times. Okay, so a function like that is also a case where we couldn't find a limit. Alright guys, so tomorrow we're going to look at some more algebraic ways of solving some indeterminate limits. But that's it for the basics for today.